I want to make this a little bit of an informal talk, so no need for the coat. It's great to be here in Brussels with history all around us. You see these? Definitely a good thing to have in history as opposed to in the present. So what I want to talk about today is a project called Apache Kylin. Apache Kylin is recently in the Apache incubator. I'm serving currently for a limited period as the vice president of incubator, but I was also a mentor, an active mentor on Apache Kylin. And the point of Apache Kylin is to bring some of the incredible performance that you can get with cubes, data cubes, to queries SQL, real SQL on Hadoop. So as I said, I'm currently the VP of Incubator, but in my day job, I'm work for MapR. And regardless of the slide color, this is an Apache talk. So I'm going to be repurposing a lot of the slides from the Kylin team. They're moving very fast. There's a lot of exciting stuff happening. The committers currently, I believe, almost all work for eBay, which is where the project came from, but they're actively soliciting new committers. So if you're interested in this sort of work, and there's lots to be done with Kylin, please drop by. I also should point out the contributions of Julian Hyde. Julian Hyde's been involved in databases for quite some time. He worked with the Drill project to adapt his query optimizer, which was called Optique at that time, so that became the SQL parser and optimizer under Drill. Then we spun Optique out as a separate incubator project. That's the Apache Calcite incubator project. And Julian has since then been contributing to a large number of, several projects, including Hive, including Drill, including Calcite, and Kylin, to bring the advantages of Optique, now Calcite, to these things. And you'll see some of the power today of Calcite. So that's actually a secondary message in the talk here. And Julian needs a little special call out because he's really been contributing a lot in his short stay in Apache. So I'm going to start talking about what Kylin is, what its intent is. I'm going to talk about the technical highlights of how it does, some quick notes on performance, the standard sort of bar graphs, and then a bit of roadmap. That's a lot in 40 minutes. So a Kylin is a little dragon. In fact, there's a Kylin outside in the square, a statue which is an Apache Kylin, or not an Apache Kylin, just a Kylin. It's a little dragon, kind of a chimera, like a sphinx. But Apache Kylin is an OLAP engine, online analytical processing for relational data. It was open sourced quite recently, but it's been in development for almost 2 years before that at eBay, and it was accepted just a month after that, and they're about to do their first Apache release. They've done releases in the past, but this will be their first Apache grade release. Now, the rationale here is that, I mean, this is the obligatory big data slide. More and more data is coming. There are limitations in scalability, in available business intelligence tools. People still want to do roll-ups. How many people visited on this day? What about that last month? What about to this particular web property? What about from that location? Things like that. And there have been some real challenges trying to adapt Hadoop to that. Most of the analysts are SQL savvy, and so that's the preferred language. And most of the data, not most of the data, many of the data sets are becoming large enough that scanning them is no longer really an option. So the goal here is literally on tables of billions of rows to tens of billions of rows. We want sub-second query response. We want to be able to group by and summarize these things. Now, the queries that we're talking about here are typically analytical drill down sort of things. We're going to draw a map, and it's going to show how hot each state is, things like that. It's very heavily oriented around grouping and accumulating using associative operators. But this is a big chunk of very important queries. It's not all of them, but it's something like 80% of the typical workload of a data warehouse. We want to support high cardinality. So for instance, if you just have gender, 5 standard genders in most census organizations, or zip code. There's only 30,000 zip codes in the US, but you might have even higher cardinality things that you want to group by, say IP address. We also want to have lots of concurrency in the most expensive parts of the operations, and so we want this to work against distributed systems. Now, there's a couple of different ways that this could have been done. It could have been done just to build it entirely from scratch. This is a grand tradition. We all suffer from this syndrome of not invented here. Well, I could do it better. But it really doesn't work when you're trying to do a significant fraction of SQL. If you look at Hive, even now, Hive is not standard SQL. It's coming closer and closer, and with the adoption of Calcite as the primary parser, it probably will become standardized SQL, but it has taken many years. I saw the first demo, I think in late 2007 or sometime around then, where Jeff Hammerbacher walked the whole hug over to Facebook, and he showed the first incarnation of Hive. And it was nothing like SQL back then. And it has slowly merged into becoming real SQL, but it has taken 7 years to do this. And that's typical design time if you really want to cover a large fraction of analytical SQL and do it right. There are some extreme subtleties in the way people write queries, and it's a huge distraction. It's getting away from what Kylin wanted to do. Now, that could have been to patch Hive. But Hive is extraordinarily difficult to patch with different semantics. And the optimizer in standard Hive is weak. It'll be better soon. And it isn't standard SQL anyway. It doesn't do a lot of the things we need. So these were possible strategies. And instead, what they decided to do was use Calcite as the SQL core. That provides the parser, provides an interpreter for that, giving you a good execution plan, has a decent cost-based optimizer, and it even has a simple code-generating executor for functional aspects of it. If you want to compute the sine +3 of some function, that little expression there, there's an interpreter called Rex inside Calcite, which will do all of that. It also provides very nice linkages to other Apache projects, notably Drill, and I'll talk a little bit about that linkage later. The strategy they're going to do, that they've done, is to build the cubes externally to hell with latency. We'll just do that, assume we have cubes already built. That's a big and ongoing sort of process. And then we're going to see what we can do given the cubes. And potentially at some point integrate with Hive or Drill or whatever the next great Apache project is. The basic idea here is queries in SQL range from right now type queries, update last visited status for one person. That's an OLTP sort of query. It's a small, and often it's a mutation of a very small row set. At the other extreme, we have tell me what the 10 most common places that people came from who bought dog collars in the last 37 days. So we now need to aggregate across these things. We need to analyze a large amount of data. Those are OLAP types of queries. And there's a continuum between these things. And very often with the high-level OLAP query, you say, oh, well, what about this place? And you open that up, and you dig in. And you have a less OLAP-y query, and you dig in, and you dig in, and you dig in, and you go down and you find the actual transactions. And ultimately, you're asking for one row at a time, and you're not doing OLAP anymore. You're doing typically OLTP sorts of things. Now, it's going to be hard to do this. There's a huge amount of data. We are going to be doing very large joins of star schemas, and it's just going to be hard to do. So cubes are the standard technology for doing this. I'll talk more detail about that. But the idea is we start with a simple table, which has been fully joined, has all of the measures and dimensions rationalized out. So we have a very large table that's already been joined. And say we have, in this case, an amount, revenue, and we have a number of other qualities. The revenue is a thing called a measure. It's the thing we're going to aggregate. The others are dimensions. They're the things we're going to group by. Here we have 4 of them: time period usually, item, location, and supplier. We want to be able to group on any combination of those. Group by supplier by week, things like that. And so the idea is that we're going to build new tables, each of which is called a cuboid, which represents most or all of the aggregations and groupings that we want. So you can see some examples there. I have query sum the revenue and the max of the revenue, and give me the supplier, but group by time, item, and location. You can see I'm grouping by 3 of those, retaining 1 of them. I could group by all of them and retain all of them in the query, and so on. Now, I might want to be doing actually something like this. I want to sum revenue, and I want to get the city from the join with location details. So the actual location up here does not actually have the city in it, and it doesn't have the state in it. So I want to use this location details table, and I want to do restrictions on that. And then I want to group by city, not by location. There might be many locations per city, but I could still use the cubes. If my optimizer were very clever, it would be able to see through this fact, and it would say, oh, look, I've got a very tight relationship between city and location, so I can find all of the cities in Minnesota. I can restrict the cube query to that, get all of those locations in Minnesota, do an actual query, kind of a nested query, where I group by location. This is obviously a cube kind of thing. And then I'm going to join with that and then do my restrictions out here. Or I might even push the restrictions into here, I would say, where location is in this Mongo list. That's the kind of transformation we want the system to do. Now, this doesn't work. I don't know why I told you. The reason it doesn't work first is because the number of cubes is exponential in the number of columns that we want to work on. Well, that's bad. And if we have a large cardinality in one of those columns, then we have a gazillion cubes. And we're not only exponential, we're exponential with a very large base. So that's bad. And skewed data can make the cubes ineffective because we have no data for almost all of the values in the cube, and all the data fits in one value. Well, what good is the cube then? So, and the magic that we have available might be insufficient to rewrite the queries. We might have to rewrite them by hand. All of these are why it won't work always. It won't be a magic bullet. It won't be the final answer. But building these cubes, we can build some subset of the cubes. This is a picture of a hypercube that we have 4 variables like we talked about, and there's a binary number according to the presence or absence of the cube, or of that dimension in the group by characteristic. And so you can see all of the possibilities there, but the cool thing is we could first group by all of the variables. That'll give us a very big cuboid table with very small amounts of aggregation. We can then aggregate from that to produce 4 other tables where one of the variables is no longer in that. So before we had all of those things, all of the combinations of our 4 variables as distinct rows in the cuboid. And now here we're going to have all of the combinations of those 3 variables in the cuboid. They'll be much smaller than the original data. And hopefully this will be smaller than the original data as well, but these will be smaller still. And then those could be used in many different ways to provide second-order aggregations, and then third-order aggregations, and finally, complete aggregations. This is the strategy that cubes are built with, so we almost only have to pay the big scan cost once. From there, we're doing smaller computations. We're still doing very, very many of them, but then the next step is from all of these different, so we might have a value, for instance, where all of those are specified. We might say put a star, meaning group by that. We only have 3 left. These are examples of the labels on the different cuboids. Ultimately, then we have milk in all the different places. But the next idea is that we don't necessarily have to build all of the cuboids. We may not have to do all the possible queries. It's very often true that some queries are interesting and many others are not. And if you have a new kind of query that's interesting, then you file a request, and 2 days later you can do that query quickly. And that leads to kind of an opportunistic sort of thing. This is a restatement of the other thing, the previous graph, in much less readable form, but it looks more relational, so it makes different people happy. The previous one makes mathematicians happy because, oh, it's a lattice. This one makes relational people happy because, oh, it's a database. It's the same stuff. But then the next trick is that we want to group these and minimize this. So here's the way Kylin does the computation. It starts with Hive, and I'm sorry, this is the actual way it computes the queries. So what happens is queries come in from the top, either from SQL sort of tools via JDBC or ODBC, or through a REST interface, goes to a REST server in either case. ODBC and JDBC translate to REST, and there's the query engine. The query engine runs on one machine, wherever the web server that's running it lives, typically a Tomcat. And the query engine then sits there and tries to rewrite the query. And the cost is kind of this huge cliff. If I can rewrite the query to only refer to cubes, I win. If I cannot write it that way, I lose and I punt. And it throws the entire query over to Hive in this sad case where for some reason it was unable to deduce a cubable query. If it was able to deduce a fully cubed query, it throws it to the OLAP cube, which does an HBase query of a special kind and does any additional accumulations. Now, this is a sad thing because it's very, very often true, like in that example I gave with the nested query, where you could do a hybrid. Most of the query could be attacked using cubes, and the result could be attacked using conventional query techniques on a single machine. It's not really that big a deal to find all the locations in Minnesota, for instance. And then you inject all of those locations in Minnesota into the cube query, and now we've got a fully cubed query. So almost all of the work is cubable, only a small fraction is non-cubable. And this is, in particular, one of the key integration paths for drill, because drill allows data sources to express rewrite rules for how much of the query could be pushed down to them. And so drill explicitly supports this sort of hybrid computation without having to make this all or nothing type of decision. Anyway, there's an offline path where Hive builds from the star schema data through a cube engine, which does a number of other MapReduce steps, builds the OLAP cubes. And that's an offline path, typically updated once an hour, once a day. Very, very long latency on that path, but nobody much cares because the data is up to date enough. And in the context of eBay, they've always had troubles getting daily results. And so if we have cubes that suddenly let us do seconds queries and it's updated every hour, it's a huge improvement. And there's a lot of business processes that fit that sort of thing. So Kylin depends on and works with a lot of the Apache infrastructure. It is not a standalone thing. It uses Hive, uses MapReduce. It could be using Spark soon. It uses HDFS or whatever HDFS-like store you have. It uses HBase, again, or whatever HBase API is available. It uses Calcite. All of these are other Apache projects, and that's really nice. That's what let these guys get to these results. Now, the results are it can do OLAP queries at blazing speed. It provides an ANSI SQL interface. Now, there's two concepts with SQL. One is compliance, and the other is coverage. Now, insert, for instance, here makes no sense. It's an OLAP sort of world. You don't insert the data with an OLAP query. You insert it by some other path. So it has limited coverage to OLAP kinds of queries, but it's very compliant within that coverage. It interacts very well with things like Tableau or business objects or MicroStrategies. It is very interactive because the queries are very, very fast. And users can define the data model and they can pre-build in very flexible ways. It does compression on the data that goes into HBase, does incremental refresh of cubes, long list of very cool features. And these come from the production setting of the original thing. Here's some screenshots that are, wow, these are really not real readable. But there's a wizard, for instance, that takes you through 7 steps of designing the cubes. You say, here's the database that I want to cube. Here's the star schema that I want to be able to do queries against. That's the first step. Then you define the dimensions in the cube. This is pretty straightforward. But then you do sort of things. You start editing the measures. You start specifying which aggregations you want to do on which variables. And you then do things which are called dimension groups, so that you have exponential growth within the size of the data in the dimension group, but you have summations in the sizes across these groups. Ultimately, you get a database design with the cuboids out the other side. In order to build this, you have an entire system which manages these jobs. When you specify your cube design, you also specify a schedule under which the system will go find new data and build incremental cubes to design that. It's a full job management system, from specifying the schedule, specifying which cubes, specifying what sort of interactivity or incrementality, and ultimately bottoming out into the all too familiar Hadoop MapReduce interface. So you can go all the way down to that level. Very nice, very efficient, and sophisticated relative to business users' needs in terms of the job management. It also has basic visualization techniques built in. You can have a schema, you can build queries on it, you can execute those queries typically very fast. If it's cubable, you can inspect. This is the query plan over here on the side, and you get results out in grid or graphical form. So it actually handles a lot of the needs of basic querying right there. That's pretty cool, because that gets you a long ways down the first level of needs, the 70%, not quite the 80% solution, but a lot of needs are done there. Then it integrates with tools like Tableau in the ways you'd expect. First, there's a setup for the ODBC connection. You have to say what schemas that you're going to be attacking with that ODBC. You then start talking about which measures are visible. And then from that setup, you get to see standard sort of Tableau interface. And these data look just like a real table, even though they are being compressed heavily. And the query is actually happening in Kylin, not in the normal sort of SQL interface. So what that leads to is multiple points of view against the same data. And this is an important property. Not everybody cares about the same things. The end user really wants a simple view of the world. They think of it as a star schema. They have no idea about cubes, and they don't want to know. The cube modeler, the administrator of some person, cares a lot about cubes, but they don't care much about the underlying administrative storage. The administrator, of course, cares a lot about HBase support and how HBase is running. Is it overloaded? Is it on the right side of hardware? Are there noisy neighbors, and so on? And this system very, very nicely segregates those views. Different users don't see details that they don't care about. The cube modeler does the cube setup that we saw and the scheduling. The admin might talk about the scheduling a bit, but would designate which HBase, and the users would see that final analytics display, not the cube building display. Here's a bit more on the process flow for things. You start with your original data, you build dictionaries against the dimensions, and you use Hive to join all of the star schema out into a denormalized form. From there, you use the joined form and the dimension dictionaries through a step of MapReduce. So here it builds the order in cuboid. It then aggregates that into the next level cuboids, aggregates that into the next level cuboids by a sequence of MapReduce steps, leading to that very tiny one on the right. All of these cuboids are then glued together with a MapReduce program which generates H files, which are suitable for bulk import into HBase. If you started with, I'm going to build these, this is a repeat, you don't need to take a shot. I just stepped back. Yeah. You're so good. If I use a camera, I lose my brain, and I just start taking stuff. But anyway, if you wanted to build this just from the description, this is almost the only sort of design that you would come up with. The only trick is that progressive accumulation from the accumulations, not from the raw data. The storage inside HBase is relatively straightforward. Each cube has an ID based on which dimensions are ignored. And so the key has the cuboid ID, the actual dimension values that are non-trivial, and all of the measures that make sense. Now, the trick here is that the cuboid ID is built, and in general that's built, using a trie that's an auxiliary table so that we can scan very fast using those IDs, and there's a coprocessor that's used so that we can have a very compact ID with very complex semantics. The semantics are of a trie, which is kept in memory, and so then the IDs can be scanned, and it can be doing a very large-scale scan on very complex criteria, but with the full speed of HBase scans. The amount of scanning that's done is still quite large for many queries. You may look at millions of rows of HBase, but it's being done in a very parallel way. So here's an example, and I think this is going to be much more useful for reference later, but this is a realistic production query that Kylin was done against. And when you look at the calcite plan, you see the prefix there. I mean, this is the important thing. Every operation here ultimately goes to a physical operator, which is an OLAP operator. It's going only against cubed things, and that's what gives the speed. You can also see inside here, by the way, there are expressions in there, like a case expression and things like that. I can't spot many others. Here's an equality test. These are the sorts of small expressions that the interpreter inside calcite can be very useful for. Now, when you want to really make it work, you don't want to build the full cubes. You want to build smaller ones. And so this is where these ideas of aggregation groups come in. Instead of 2 to the n plus m plus l, where these are the number of dimensions in each of the subgroups, we use each one separately. And so we're going to query with this pattern or that pattern or that pattern. We're never going to cross over these things because that would resolve to a Cartesian product that we didn't retain the information for. And that really makes a big difference. It makes the difference between 1 billion and 1,000. So big win. And million X in space is a good thing, even with big data. This talks about the incremental cube building, which I described earlier. So let's talk about performance. And we're now going to talk, and this is going to be the obligatory bar charts, but this one's a little bit different. Now, there's 5 queries mentioned there where they give the actual details, but the bar chart's more interesting. It only talks about 3 so that it's more legible. The fact is, there is a green bar here. And there's a green bar here. Here you can actually see the green bar. So the speed up varies quite large factors, but is commonly in the factor of hundreds to thousands. Now, this isn't a fair fight, but whoever engages in fair fights in computing, it's not doing the same computation. So it's no wonder that it's not taking the same amount of time. It's cheating. And all of the work that Hyde did is being done offline and hidden from the user. So you've kind of dehydrated the queries, and so you only add water at the end, and bang, you have your strawberry or whatever without having to grow it. So somebody else is growing the strawberry. Somebody else is doing this work, that Hive is doing, but it's happening in the hourly builds for the cubes. And in fact, much more work is being done because it's being done for all the possible queries you might do. But users care about this number, not that number. that number, the building in the background, goes into the quarterly budget or the annual budget for buying more machines. This budget comes out of my life. So I care much more about, does it take a quarter second of my life, or does it take a bunch of your budget? This is the way people make decisions here. And so, but it illustrates the value. It really, really can be highly interactive. Instead of minutes for these queries, it's fractions of a second. And you can see a lot of the statistics for how Kylin is working. You can see how the scale out works. You get essentially linear, although with a non-zero intercept, so it's not exactly right, so that the latency goes down with increasing things, the throughput goes up, all the sorts of things that you want. The reason it has a non-zero intercept is that there's some overhead of planning the query. That's not improved by parallelism. This is Amdahl's law. You can look, this is production information from eBay, and the 95th percentile time over this, even with some naive users who kind of screwed up in here. They didn't screw up very long. They learned, don't do that. Don't do things that don't cube well, or go talk to the administrator so they can fix that. But even then, the 95th percentile was under 5 seconds. I would kill for that some days. And after people were educated, the 99th percentile, the 90th percentile was under 5 seconds. The 95th was still quite short. That's 10 or 20 seconds. That's still doable. So here's the roadmap. And this has the great vertical bar, which is now. From 2013 to now, they've built the prototype for the OLAP engine. That's what we've seen. All of the incremental refresh, all of the GUIs for that have been built. They're in the process right now of also supporting OLAP. These are subtle differences in how OLAP cubes are kept and built. The streaming OLAP is being worked on right now. I think the JDBC driver may be already available. The new UI is not ready. The Excel support, I think, is in place, and so on. You know, it's work in progress. And then the next generation, they want to see more automation, more capacity management, more ability to trade off different things, integration with more advanced offline engines like Spark, and integration with systems like Drill that have the potential for integrating the plans in a more interesting way. The ecosystem is fairly mature, far more mature than you would expect from an incubator project. It's usable in many production settings right now and supports a lot of the life cycle of cube management. And that's because it was taken from a real production need. This is a slide I kept, happy poster sort of impression. But more important is questions that you guys might have. I'm sure there's a few. Good, yes. This is the kind of thing that really does inspire some questions. You? So the question is, will it extract dimensions from denormalized data? Now that's another place where Drill would help a lot, because Drill handles nested data, denormalized data very, very well, and presents it as if it were real relational systems. And that would allow cubes to be built against these very unusual structures, the same way that Drill allows SQL relational-only systems to have a facade over that kind of data, as if it were really relational. This is one of the real advantages for integration of that sort. So at this time, not so much, other than the limited capacity that Hive has now. And subject to the fact that you erase the non-relational aspects at the first step. And then in the end, you're still going to be limited with relational sorts of accumulations, subject to the fact that they're integrating things like the hyperlog-log approximate cardinality tests and some other things like that, which are approximately associative and can provide nice things. But Sort of yes, sort of no. More in the future, I think, is the final answer. There was a hand over here. So the question is there an interest in MDX interface instead of SQL? MDX is a kind of a machine interchange language for OLAP-oriented cubes that's generated by certain tools. There certainly has been discussion of that. The current user set of Kylin is heavily, heavily influenced by the one production user, eBay. It's brand new. Now, people have talked about that, but there are no users at eBay who have tools that profitably benefit from these alternative interfaces. So the right answer for you is, if that matters to you, join the community. That would be, hey, you laugh. This is partly my job, but seriously, this is an open community. They're really welcoming. They're actually making a big deal because this started in eBay China. All of these people are native Chinese speakers. They have variable levels of English, but they are conducting all the discussions on list in English. And that's a big step, big sacrifice for them to make in agility in order to engage a community. And so I think a natural response is to engage back and start contributing ideas and use cases and hopefully production use. That would be awesome. But so far there's no need in the sense of people on the list saying, I need to use this, I can't use it until we implement this. Yeah?
So this sounds very impressive, and so probably lots and lots of users will jump on it.
I hope.
And did you make any performance tests about the concurrency within the HBase? Will it perform well if I don't have one user, but let's say 5,000?
So the question is about concurrency and how it's going to be handling large numbers of users. Within eBay, I think they have over 1,000 users now. That's not 1,000 concurrent users. Now, the question is, there's two strategies for handling lots and lots of concurrent users. One is to be really fast, because then you never have concurrent queries at all. And it is very good at that. The problems really come in where you have queries which don't cube well, and they begin to steal resources from the ones that do. And because it goes to two different paths, that is almost a non-issue. In fact, in practice, the Hive path, because the users who are using Kylin are so attuned and so very much wanting sub-second responses, if it goes to the other path, you might as well just put up a red thing saying, this is going to be really slow, you probably don't even want to run the query. Because that would be what most of the people do. They just kill the Hive job after it starts. In other systems that use calcite, concurrent use is fairly effective. It works pretty well. The sophistication that something like Oracle has in terms of resource limitations do not exist, but in this case, because of the fast queries, you do pretty well. You can also instantiate multiple Tomcats which handle most of the work. The parallel work against HBase still is substantially there, but concurrency there works fairly well because it's fairly perfectly parallelized against a very simple scan. And so, subject to how well the file system is going to serialize large reads, it should run fairly well. So, they have not had problems. There have not been formal evaluations. Summarized answer. Yeah, no problems is a good answer. But it's very qualified and not a real answer. So we have enough for one more question.
What kind of authentication and authorification?
Come now, this is a dupe. Essentially none at this time. And the user authentication path that will probably be followed is to secure the web interface. Now that leads to problems with ODBC and JDBC and so on, for which there are alternative authentication paths which could be driven into the web interface. But as we all know, authentication between different ecosystem components in Hadoop is a very thorny problem and an inconsistent problem. There's no exception here.
JDBC side?
I don't think there's a good answer there other than providing credentials in the JDBC URL, which is the same horrible answer we've been dealing with for decades. There is no work currently going on to do impersonation of different users or things like that. If it integrates with a more advanced system, Hive has some facilities for that. Drill is about to have some facilities for that. If for instance, Kylin became a data source underneath Drill, then it would inherit all of the authentication and authorization framework from that. If it could, as Hive adopts Calcite, it might be integrated in a similar wise for Hive, and again would inherit those good properties from the overall system. But right now the answer is to laugh in your face. And that's sad, but it's still a large use case where some people can stand to have non-sensitive data being queried. And then you just restrict access to it at all. Provide different Tomcats with different tables. But it's a sad answer. I'll slide you in. We just went over, but
Just a simple question for the performance. So in one slide, you compared the performance of Kylin against Hyde. So for that, which computation did you use for Hyde? So Hyde on test or Hyde on just normal memory?
doesn't matter. I mean, it's not going to be 1,000 times faster. It was a recent version of Hive, but it was not a bleeding edge version of Hive. So I don't know. But the fact is, it's going to be blazingly faster. You were supposed to laugh on that slide, not take it seriously. Okay, well, I'm going to be talking again in time. We really can't. We're 2 minutes over now, and I have to get some lunch before I talk again. I'm going to be talking about 19th century open source big data as part of my time series and the internet turning upside down talk that's at 3 something. So I'd love to see you all again. Let's do that.